We know from the theorem that we had up here on the board in the previous lesson that, in particular, A is invertible if and only if the determinant of A is not 0. Right? So this is something that was part of the big 6-part equivalent theorem. And what I want to discuss now is a certain construction called Adj. Adj stands for the word adjugate, although there are other terms, I'll discuss it in a minute, which is a way of writing A inverse, explicitly when you know that the determinant is not 0, which is an if and only if statement. Okay? So here's the construction. So let A be an n by n matrix. And the construction of Adj A does not depend on the fact that the determinant is 0 or not. The statement about constructing A inverse is. Okay, so we'll see it in a minute. So I'm starting with any square matrix, n by n matrix. We construct a new matrix denoted by Adj of A. Okay. Now this word Adj used to stand for the adjoint of A, or there was one other thing, I don't even remember, but classically I learned it as the adjoint of A, but the terminology today is usually that this is called the adjugate matrix, where the adjoint is reserved for something else. So let me write it here, Adj for adjugate. How'd you like purple? Blue with the touched red previously and has a touch of purple. In fact, I have a purple here. Right? Whatever. Okay. It is blue, though. It's blue. It's blue. Okay. So Adj A, we construct a new matrix, Adj A, as follows. So it's mysterious, right? Wow, what is this Adj A going to be? So a matrix has entries. I'm going to tell you what is the ijth entry of this new matrix. Okay? So the ijth entry of Adj A is the following. I take M, we denoted by M the minor. Okay, so I'm taking the minor. Once I have an I and a J, I can find the minor corresponding to I and J. Cross out the jth column and the ith row, right? That would be Mij. Okay, but I'm not taking Mij, I'm taking Mji. Okay, so the ijth entry of Adj A is take the determinant corresponding to the crossing out the jth row and the ith column of the original matrix A. We call that the jith minor. And there's going to be also a sign. So it's going to be minus 1 to the power I plus j. Okay. So the first question you should ask, what is this? So let's do an example. And the second question you should ask is, what the is it good for? And we'll see that. That's the theorem that's going to follow. Okay. So first of all, example how we calculate something like this, and then the theorem that shows why it's useful. Okay, so here's an example. So let's take a 3 by 3 matrix. It's going to be 2, 3, negative 4, 0, negative 4, 2, and 1, negative 1, 5. Just a good old 3 by 3 matrix. And let's calculate its Adjugate, the corresponding one. And why am I making it so big? Right, each entry is going to be a 2 by 2 determinant, right? Okay, that's what it means, taking the determinant of the minor. Okay, so each entry here, there are going to be 9 entries, each of which is a 2 by 2 determinant up to plus or minus, right? Okay, so the first entry, the 1, 1 entry, is the minor corresponding to 1, 1. So it's this minor here, right? Cross out the first row in the first column. It's this minor here, let's write it, negative 4, 2, negative 1, 5 determinant, right? That's M11. And now I need to decide if there's a plus or a minus here. So it's minus 1 to the power 1 plus 1. So there's no minus, it's a plus. Do you agree? What about this entry here? Okay, so it's the 1, 2 entry. So what I'm going to write here is the 2, 1 minor, right? I'm going to cross out the second row and the first column. So I'm going to get 3, negative 4, negative 1, 5. That's the corresponding minor. Do you agree? And then I need minus 1 to the power 2 plus 1, which is 3, so there's a minus left here. Do you agree? Okay. And now over here, this is the 1, 3 entry. So what's going to sit here is the determinant corresponding to the minor 3, 1. Okay, so 3, 1 means cross out row 3, column 1, you get this one. 3, negative 4, negative 4, 2, determinant, and it's going to be a plus. Do you agree? Okay. Everybody good? Is it clear how I got this? Let's do this entry here, for example. This is the entry 3, 2. 3, 2. So 3, 2 is going to be the minor corresponding to crossing out the third column in the second row, right? M2, 3. So it's going to be 2, 3, 1, negative 1. 2, 3, 1, negative 1. And 3 plus 2 is 5, negative 1 to the power 5. There's going to be a minus here. Good? So I'm going to fill in the remaining 5 and not calculate them manually, because I think you got the idea. Okay, and check and tell me if you agree. So I get here 0, 2, 1, 5 with a minus sign, 2, negative 4, 1, 5, 2, negative 4, 0, 2 with a minus, 0, negative 4, 1, negative 1, and finally 2, 3, 0, negative 4. Good? So each one of you pick one of the remaining 5 and verify that I did it correctly. Okay? Good. Good? Okay. So, okay, we're not going to leave it like this, right? We can now calculate it explicitly. So what do we get here? No space left. So let's do this. Let's do this. So Adj equals, and now let's calculate these numbers. So it's minus 20 minus minus plus 2. So it's minus 18 here. Right? Everybody knows how to calculate 2 by 2 determinants. Here we have 15 minus minus minus. So it's minus 15 minus 4. it's 11, but with a minus, so we have minus 11. Good? And I'll fill in the rest. Minus 10, 2, 14, minus 4, 4, 5, and minus 8. Good? So is it clear what the adjugate matrix is? And obviously, given a matrix, finding its adjugate matrix, if the original one is 3 by 3 or higher, there's going to be some work here. Okay? It's not something that comes for free. It's not like doing a single row operation or something like that. There's work. Okay? There's technical calculations to carry out. Okay? Okay, so now we know what it means. Now the question is, what is it good for? Okay, so here's a theorem. Again, I'm not going to prove this theorem. I'm going to show you why it is convincing. Okay, so what is convincing, I'm going to show you on the example that it seems to work. That's by no means a proof, of course. Okay, but what I'm going to be interested in is, in fact, the corollary to the theorem. That's the useful part. So the theorem says that if you take A and multiply it by its adjugate matrix, these are two n by n matrices, we can multiply them, what you get is the determinant of A times the identity. The determinant of A is a scalar. This is a number. So this A times I is just a different way of writing the matrix which has the determinant along its diagonal and 0 in all the other entries. Do you agree that this is A times, determinant of A times I? Okay? So that's this theorem. I want to convince you, at least partially, why it's true. You can, of course, check in the example. You can multiply. We calculated the adjugate matrix of A for a given A. You can multiply them and see that indeed that's what you get. But let's be convinced, at least for the diagonal entries, why each one is indeed the determinant. Why these are 0 is a bit more mysterious. But why the diagonal entries are the determinant is rather obvious. So let's look at the example. Let's look at the example here. So if we multiply these two, okay, what would be the 1, 1 entry? The 1, 1 entry is the first row of A times the first column of B, or B here is, what was this? Oh boy, 0. B here is adj A, right? So it's the first row here times the first column here. That's the 1, 1 entry of the product. So what do you have? You have 2 times this, which is precisely the corresponding minor, plus 3 times this, which is precisely the corresponding minor, right, with a negative sign, minus 4 times this minor. Do you see that? And this product is precisely the determinant of A, right? That's how we calculate a determinant. We choose a row and multiply the entries times their corresponding minors with interchanging signs. Do you see that? Okay. So do you agree that even beyond this example, do you see that when you take, for example, row 3 times column 3, you get precisely the determinant of A? 1 times this minor, there it is, plus negative 1 times this minor, there it is, in a minus sign, which is sitting here exactly for that reason, and so on. Does everybody see that? Okay, so when you take a matrix, multiply it by the adjugate matrix, by the way this was constructed, you get the determinant along the main diagonal. Okay, why you get zeros in the off-diagonal entries, you have to see that in the proof. It's not as obvious, right? Why? How did it mysteriously happen that, for example, let's take the second row times the third column, 0 times negative 10, minus 4 times minus 4, which is 16, minus or plus 2 times negative 8. You really get a 0, but that's not obvious from this construction. Okay, it requires proof. Good? Okay, so that's this theorem without proof. And here's the corollary. So everything we said so far does not depend on invertibility and the determinant being non-zero. Okay? What I'm going to do now is I want to divide by this. This can only be true if A is invertible, which is if and only if the determinant is not zero. So this is the corollary. If A is invertible, then we have the following statement. A inverse is 1 over the determinant. This is a non-zero number if A is invertible. This is just its reciprocal times Adjugate. Okay. So why is the corollary true? Proof of the corollary based on the theorem. Okay, again, I'm doing the easy part. Proving the corollary based on the theorem. So if A is invertible, then we know that the determinant of A is not zero. That's the statement we started this lesson with. Therefore, we can take this theorem and divide both sides by the scalar det A, the determinant of A, right? Therefore, 1 over the determinant of A times Adj A equals just the identity matrix, right? And now we can multiply both sides by A inverse, which exists because A is invertible. So if I multiply here by A inverse, I just get A inverse, right? And if I multiply this side by A inverse, the scale, so I'm multiplying here by A inverse. This is a scalar. I can move it out, right? And I get A inverse times A. What is A inverse times A? I, right? So, and what is I times Adj A? It's just Adj A. So I get exactly what I wanted. 1 over the determinant times this matrix. Good? Okay. So that's why this has the title corollary. Okay, it really follows as a one-liner, except that I write with big font and therefore it fits as 2 lines on the board. But in your notebook, I assume that this is 1 line from the theorem. Okay, what's hidden here is the proof of the theorem, which is more involved, and we skipped it. Okay, good? Okay, so here's homework. Here's homework. You know what? Let's do it. Let's do it. Let's take the previous example and find A inverse using this theorem. Okay, let's do it. So I'm going back to this example. This is A. I already did the work. Okay, the work was finding Adj A. There it is. And now I want to find A inverse. So A inverse would just be, I still have to calculate the determinant of A itself, and then I need to take its reciprocal and multiply it by this matrix. Do you agree? Okay, so let's do that. So example, continued from previous example. Okay, so what's missing in order to use that theorem that the corollary that we just wrote is we need to find the determinant of A. That we didn't do yet. So the determinant of A is what? So I'm rewriting what A was. 2, 3, minus 4, 0, negative 4, 2, and 1, negative 1, 5. You can just choose your favorite row or column and calculate the determinant. Or we know we can do some operations as long as we pay careful attention to how they mess up the determinant. Okay? But for example, we know that if we add a scalar multiple of one row to another row, that does not change the determinant, right? So I want to add or subtract, add minus 2 times the third row to the first row. Okay? And that would put a 0 here, right? If I subtract 2 times this row from this row, I would get a 0 here, and then I'm going to develop the determinant using the first column. Okay? So in a 3 by 3 determinant, all these shortcuts are not necessarily shortcuts, but if you take a big determinant, sometimes the shortcuts can have you calculate a single. If you start with a 17 by 17 determinant and you take a little shortcut, you can find yourself calculating one 16 by 16 determinant rather than 17 of them. That's a serious shortcut. Okay, so let's do R1 minus 2R3. Okay, and this is an operation that preserves the determinant. Okay, so the determinants remain equal. So I get 0, 5, negative 14, and 0, negative 4, 2, and 0, negative 1, 5. Right? Yeah, that would be stupid. Sorry, thanks. Good? Good? Okay, and now I'm going to choose this column. That was the motivation for doing this move. I'm going to use this column to develop it. So I only have a 1 here, and it comes with a plus sign. 1 times this minor. So I just get 5, negative 14, negative 4, 2. Good? And then this is what? 10. Oh boy. 10 minus 4 times 10 is 40, 56. 10 minus 56, so it's negative 46. Wow, really? Really? Good? Okay. And therefore, now that I have the determinant, now I can write down the inverse. A inverse is 1 over the determinant, so 1 over negative 46, times the adjugate matrix, which we wrote over there. I'll just copy it from here.
Minus 18.
Negative 18. Don't read it. I got it. Thanks. 2, 14, negative 4, and 4, 5, negative 8. And if you really want to plug in the numbers, then the minus here is going to invert them, and you're going to get what? 18 over 46, 11 over 46, 10 over 46. You can even simplify some of these. 2 over 46, 14 over 46. No, these are with minus. 4 over 46, and negative 4 over 46, negative 5 over 46, and 8 over 46. This is A inverse. Okay? So this I'm really going to leave as homework. Well, the easy part is verify that this is A inverse. The way to do that is to take A, multiply it by A inverse, and see that you get the identity. But on top of that, for practice, find A inverse using the previous method that we discussed for finding the inverse matrix. Namely, set A alongside I, and then do row operations on A until A becomes the identity, and whatever happened to I is going to be A inverse, right? Remember that? Okay, so do that and see that you get the same thing. And you're going to say, wow, that's a lot of work, right? Taking a 3 by 3 matrix, putting it alongside I, and then doing all these row operations. That's a lot of work. Isn't this easier? Well, the answer is not necessarily. We worked for 2 boards on deriving this because we had to work to find this matrix, the adjugate matrix, because it was a bunch of 2 by 2 determinants, right? That's the entire previous board. Okay, so both ways are, in fact, require some work. And I would even say more. Let me just write the homework. Find a inverse using AI. So everybody understand what I mean by using this thing. Okay? And see that you get the same thing. So the point is that I'm not saying that what we just did is easier than this. In fact, I would guess that this is easier. Okay? So why did I just spend time on presenting all this? So this thing does have one pro compared to this. This is an algorithm. It's an algorithm. It's a recipe telling you, okay, A is invertible. Here is how you find A inverse. Do this. Okay? You know that after you do it, you're going to get A inverse, but it's only an algorithm. Whereas this over here is a formula. Look here, please. This is a formula. This is a concrete statement of what A inverse is. And when you do proofs, for example, or do calculations, you can substitute, when you see A inverse, you can substitute this into whatever bigger formula or bigger argument you're working on and continue from there. Whereas if it's an algorithm, you can't substitute the algorithm into a calculation or do you understand the difference? Okay? And several things we're going to see, and I think even some things we already saw, have the advantage of being able to write something like this over saying, hey, here's how you do it. Okay? Although sometimes the here's how you do it part may be shorter. Okay? Clear? Okay. So honestly, I don't calculate inverse matrices like this. I always do the previous way, writing A alongside I and doing the row operations. But this is useful, especially in theoretical statements, where you can just substitute this for A inverse. Okay, good? And in fact, the next topic we're going to discuss, something called Kramer's rule, is another way of solving a system of equations, which we already know how to solve, right? We know how to solve a system of equations, but it's an algorithm again, right? It's a bunch of row operations you do at the end of which you get the solution, right? And what we're going to do next is again a statement of, hey, boom, here's the solution, expressed explicitly. Okay? Not necessarily easier, but not via a statement, cloud, here's the algorithm you do. Okay? Okay. Just a couple of remarks concerning the Adj. Where will I write them? Let's write them here. I'm not going to prove them. So I'm going to call it remarks. In fact, these are properties, and we know that properties is a different way of saying theorems, and you need to prove them. And I'm not saying they're hard to prove. In fact, they're not. But I just don't want to spend more time on this. So the adjugate matrix of the identity is the identity itself. You can easily verify that. And so this is 1. And 2, adj of a product, AB, and this is again something we've seen several times and shouldn't come as a surprise, is the product of the edges, but in reverse order. Okay? And we've seen this phenomenon, for example, in the inverse, and we know that adj is related to the inverse. We've seen this phenomenon in the transpose, right? So this is not something that should come as a big surprise. Okay, good? Okay, so this wraps up our discussion of Adj A. And what I want to do next, as promised, is what's called Kramer's rule, a new method of solving systems of equations based on some techniques and notions that we now have available. So that's coming up next.